Welcome. All right, we are going to begin with regression. This is our last presentation, and we are going to look over the comparing of values to one another in both a simple linear regression and a multiple regression. So with a simple linear regression, or in both of them, we're going to look at predicting a value based on another value and looking for any significant relationships among values. So what is simple linear regression? Regression describes the relationship in the data with a line that predicts the average change of y per unit of x. So what is that saying? It's basically we're taking correlation and we're adding a line from all those little dots. So imagine a scatter plot, and we're creating a line to find some sort of association between the space in between. I should say that the space in between the line and the variables, the little dots around. So this is used to quantify the relationship between the two quantitative variables. But unlike the correlation, the regression can be used to express the function, so we'll see a lot of the functions here, between the relationship of x and y. So it does this by fitting a line based on certain points, and one challenge of this is to find the best fitting line that describes the relationship. So you can naturally draw a line anywhere, but what is the best one that describes for all the data points? Okay, so within this, we are going to basically, so here's our example here. So regression gets at relationships, but primarily we're looking at predictions. So what does X predict Y? So can we predict math achievement from grades in high school? So within that, our math achievement would be our dependent variable or outcome variable, response variable. I know all of these, so we're just sticking with dependent variable. And then our independent variable would be our grades in high school. I hope to never be a part of that test. And by doing this, just like with correlation, we are looking at continuous scales when we're looking at these variables. Okay, so a simple linear regression is, or just regression, it's a combination of correlation and Anova. So as prior instructors have stated, as well as it's in my notes, that if correlation and Anova were to have a baby, it would be a regression. All right, moving forward. So with this, this is a good visual of what is the linear regression. So what we have here is kind of it is our scatter plots, and generally we're going to have a positive or a negative relationship. Hopefully that's the idea, right? And that for every time that, in this example, every time that x increases, y will also increase. So within that, this is a function, because we're not only just looking at where this y value is, but when we add in a line, we're actually trying to find, what's going to what happens if, if this is 2 and this is 3, then where's that 2.5? Where does that y end up? What would that be? And so that's kind of where the prediction can come in. And this is a function. So in other words, that wherever x is, then y is elsewhere. All right, we use a general linear model, and we've had some practice with that. We'll have more practice with it. And this helps us better describe that relationship by finding a line that is, it's the best fitting line, and it's when we say best fitting, it's the least amount of distance between the actual value and that line that we create from this regression. So from that scatter plot, let's look at that visual again. That line is created, and so this distance here, for instance, on this top star is going to be a lot more than say this star when it comes to this line. So again, this dotted line, necessarily, say I was to like try to move that, well, then we're kind of going against the whole idea of this regression. So this is a calculation that we will, see. So we're looking at the relationship. Again, it can be either positive or negative. And when we predict these scores, because yeah, we have some scores, but we're trying to find an overall prediction for that based on our sample. So we don't use the y necessarily. We use a y hat when we're talking about predictions. So the one here is, if I know your age, then I can predict your height. Not the best example, but it gives you an idea of my x. If I know your x, then I can predict the y hat. All right. And from this distance that we're discussing here, this is a residual. And a way to remember, like, okay, where does residual come in is, this is weird, but this is where my visual brain went, is that, say this line is like a line of slugs, right? And they go off the line towards these dots. They leave this residual. Okay, that's it. I just wanted to share that moving forward. Okay, let me make sure I read my notes now. You can predict one variable from the other by examining the means. So as usual, we're looking at the mean amongst these continuous sets. And it creates a horizontal line to best represent that mean. And this is also, this residual, the variance is also known as an error. And this linear regression allows us to create another straight line that has of less of an error to make the best fit, and that is the regression line. This line is always going to be a straight line within a scatter plot, and it's going to pass through the average of all the y-scores for each x. It's like a mean. It passes through the middle of the data and has much less residual error than when predicting. So there's our residuals. Here are other examples. Here's our regression line. There you go. It travels. Okay. So with our prediction, it's always going to be between -1 and +1, just like with the correlation. And the error in prediction is related to the strength of the correlation. So this is known as the methods of least squares. So basically, we can calculate based on a given x that we can calculate where that y is going to be, and this is our equation. Like much of this class, I'm not making you do this by hand. I really want to focus on, getting our hands dirty with the data set itself. But I will go through some of the idea. Okay, so we have a y hat here, and that is our predicted value. And then we have our x over here, and that is our raw score. So that's just what we get from our actual data set within our independent variable. And then we have our A, and this is the intercept line. So this is where, when that line would reach the y-axis. And then we have the slope, and that's going to be represented by B. And that's going to give us like how steep that line is going to be or how not it's going to be. It gives us the angle and direction. And with that, you have the B. This is our equation for that. So we would find our correlation coefficient as well as our sample standard deviations. And this is the full-on equation that you would need to do. So the total number, and then you would sum the x times the y, and you can read the rest there. And then for the intercept, for the A, it is the average of y minus the average of x once you find that B. So if you were to do this by hand, you would need to find B first in order to find A. That's pretty BA. All right. Components of a regression model. So here is our slope, and this is our b. So this is what we would find first, and then in order to find that that a, you obviously, what we just looked at, you would need to do a little bit more math, more equations here to give that. But this is the line that we are really wanting to focus on for this presentation. So generally, we're only going to be focusing regressions within this class on samples. We're not going to look at the population. However, this is the equation for a population, a simple regression population model. All right, let's go. Emoji. Actually, I don't even think that's an emoji. All right, so here is a brief little example if we were to do this by hand. And okay, so we have an n of 6, so we have 6 observations here. And we have an x variable, we have a y variable, okay? So there's our 2 variables. And then we would we would sum these up, we would find the average. And so the average for our x is going to be 5, our average for y is going to be 6.5. And then you would square both of those. So here it is, 5 times 5 is 25, 3 times 3 is 9, so on and so forth. You can do the rest. And from there, this is how we would get that b. This would give us an idea of what our b, so our slope, going back to this, that's what we are trying to find within this. So our answer is 1.6 for our slope. And then to calculate a, we would take b, and now we can actually fill in the average for x and y, and we would get an a. I just got a text message from no one. It's none of your business. But we would get an a of negative 1.5. All right, so we found our a, or we found our b, and then we found our a, and then we would use a and b for the prediction. So now we plug in whatever our b is, and then we would put in the x for whatever value, as well as our a, and then we would do this for each point. So it would be, for instance, we choose an x, one of the x values was 4, then our predicted y would be 4.9 based on this calculation. This calculation right here is this. If it was 5, it would be 6.5, and so we can imagine. Let me see if I can draw on this. It's really hard. I'm doing this on a laptop because of technical difficulties. So if you were to have a line and say we do 1, 2, 3, 4, oh gosh, 5, 6, 7. Bear with me. 2, 3, 4. It's so hard. 5, 6, 7. Okay, I'm going to go on. All right, so if we have a 4, now we would put 1, 2, 3, 4, and then we would look at our y hat, and it would be 4.9. So then I'll go 1, 2, 3, 4.9. So it's like right there. Then for 5, it would be 6.5. So then I go 1 up, and then this would be 5, 6, 6.5. And then if we had 7 way out here, then it would be 9.7, so that's way out here. So we can see where these points are, and this should be the line that we are focusing on. All right, let's take this into an example that actually I believe goes back to chapter 1. It's been used every so often, but it's looking at the residuals of. Now we're looking at the residuals in smoking and lung cancer. I think we did this last week too. Yeah, we did. All right, so we have here the cigarette consumption by country right here in 1930, and then we have the mortality right here, and then just like we did, with those with that simple, just with the n of 6, we did all the calculations. Here is the exact same thing, finding what our predicted y is, and then here is our residual. So this is like how far away this point is from that line. So we'll come back to this. So for instance, let's remember that the United States of America, number one, is at 1,300, and our residual is at negative 16.4. Let's see what that looks like here. So if I look at cigarettes per capita, let's see, and I go to, let's find where the United States is. So it is 1,300. It's way out here. It's clearly number one on the x-axis. So this is our residual of that negative 16.4. Okay, let's just see what these two are. They're on the exact same x-axis. So that is going to be Great Britain and Finland. And so, although yes, they have the same amount here, but their mortality rate is different. They have a different predicted y value, and so therefore our residuals are going to look different. So it looks like this would be Finland and this would be the UK. Okay, some of the assumptions, the conditions in order for you to make an inference on this is that both variables need to be continuous, scale, interval, ratio, all of those, as long as they're numbers that can go up and that can go down. It needs to have linearity. These need to have independent observations, so they can't be related to each other. There needs to be a normality for your x value, for your x variable. And they need to have equal variance and no extreme outliers. Within this, the distributional assumptions for the linear regression and Anova are for the distribution of y given x. That's what this line is here. That means given, so y given x. So you have to take out all the effects of the x's before you look at the distribution of y. As it turns out, the distribution of y given x is by definition the same as the distribution of the residuals. So in other words, the easiest way to check for the distribution of y given x is to save your residuals and check their distribution. So we will look at residuals a bit more. Okay, another happy face. Let's go through it. We do the normal hypothesis testing just like every other time. And let's go back to the cigarette consumption. Okay, so here's our list. We've already gone through this. Per capita cigarette. I need to remember per capita. I always see the cig and I'm like, so 1,300 people smoked cigarettes? That's impressive data. No, it's cigarette or per capita cigarette consumption. Okay. So what is our null hypothesis? It is that there is no association between smoking and lung cancer. Or you could also say that smoking does not predict lung cancer. That means that there is no association on anything. And this is going to be shown up as a B. And we'll go back to this B here, here in a bit. And then our alternative is that there is an association between smoking and lung cancer. In other words, that smoking does predict lung cancer. In other words, that our B, because we're not looking at means anymore for regression, that it is not equal to 0. That means that there is a difference there. Okay, so we will practice this in class. We're going to open up this file that we have before, and we would go to Analyze Regression Linear. And we are actually going to use statistics, plots, save, and options for this example. All right, so within statistics, we need to make sure that our regression coefficient estimates and confidence intervals are there. We need a model fit. We have the descriptions, which is descriptives, which is there for us. And then for our residuals, we want to make sure that our Durbin-Watson is checked, as well as our case-wise diagnosis. So this is we're checking before. We're basically making sure that nothing is too way outlandish out there. Okay, so then we go to where did the arrow go? This should be. Did I miss something here? It should be plots. Yeah, there should have been an arrow right there. All right, we go to plots, and what this is going to do, unlike what we did with correlation, where we just looked at like an x value to a y value, now we're actually turning our values into z-scores, and we're turning in what our prediction would be as well as the residual. So we'll see what that is, and then we'll test for a normal probability plot as well. So we hit OK, and what you will get is here's our residuals. So this is basically telling us, is there anything that's like way too far out there? And this is giving us our minimum. So, and when I say way far out there, we're talking about this line here, and then we have a dot here, and our residual is this line that connects, this horrible line that connects back to the line. So our snail residue, how far away it is. And so generally we want to have nothing greater than 3.29 or nothing less than 3.29. If there was, then there would be outliers. That's what we were checking for. So this negative 1.971 and this positive 1.691 are within that range. We are good to go. That means that everything is close enough that there isn't some one way out here where the residual is just way too long. All right, so this is checking for our assumptions. So we want to make sure this is just a visual representation that and notice that this is our unstandardized residual. So what you just need to know is like how far away, again, we are from this, with the x values away from this line. And so what this visually gives us is that it should be kind of evenly scattered, just to show that there is not one easy way. This is hard because this is a small n, but when you have more, it would look something like this. So this is what we want. Cha-ching. That should be a check mark. There we go. Cha-ching. So this is what we want. However, this is showing us something much different because our residuals, there's clearly a pattern here, but notice that the residuals here are much smaller than the residuals way out here. Not only that, you know, yes, it can go below and above, but I mean, this is just all over the place. So this isn't something that we necessarily want. And neither is this one. This one is all over the place. So it doesn't matter where your x value is. The residuals can be high, low, negative, and positive. So this has this kind of arc that we're not really looking for. Again, what we want is an evenly scattered area. Here's what the histogram looks like. It's slightly positive skewed. All right, and this is our PP plot of regression. And again, this gives us a line to show where the residuals are based on our observed and our expected probability, cumulative probability. Okay, we have our descriptives, just looking at them. We have a mean of 20 for lung cancer mortality rate, and then cigarette consumption per capita, which our average is 603. Now we're going to check for assumptions within our output. And we checked the Durbin-Watson, and this is where that comes in, which our number for our Durbin-Watson, or the D-dub, should be between 1 and 3. This should say score must be greater than 1, yeah, or less than 3. All right, so we check that. We got a 2. Awesome. Sounds good. That means that everything is independent amongst the observations, that there's nothing too absurdly close from your samples. So then we look at the correlation, and if things are correlated, then that's kind of our bouncer in a sense. That means that there is something up, that we should move forward with this and see what we get. So again, the R is the correlation here. So we have a 0.737. So that's a pretty strong correlation, so a high degree of correlation. And then our R squared and adjusted R squared, this gives us the total variation in the dependent variable. So within our example, we're saying that, and we turn this into a percentage, so we would say that 54% of lung cancer mortality rates can be explained by cigarette consumption. All right, and that is pretty large. Now, the adjusted R-square, this is used more to be more conservative. So if there was a number, if you were to publish something, it's better to put the adjusted R-square. All right, and so we looked at our R and within our effect sizes. This is just, again, a supplementary documentation for you. And we were at a 0.7, it was above that, so it's much larger than typical. Ooh, that's good to know. It's like, all right, we're on to something here. So this significance, what this is showing us, and this is just basically a t-test, it tells you that if by adding the variable, it improves the predicted ability of that model. So in other words, we're saying that our model is strong. Okay, then we look at our coefficients, and there's a few numbers to look at here. We will start off with this constant. You will always have a constant here because this is looking at our y-intercept. All right, so if we start over on the significance, because we always want to look for significance, then you would see that there is not a significance within our constant because this is above 0.05, right? It's 0.2, so it's well above it. And what this is showing you, when you since we have a p-value of 0.202, the constant is not significant. Therefore, we cannot conclude that our a-intercept isn't 0. We don't have enough evidence, in other words, with this number right here, we don't have enough evidence that this actually could be 0. If this was significant, then we could say that this number would be, it could be in the realm possibility of reaching 0. So what is the 0? Well, it is, again, it's looking at the y-intercept and saying that if y was 0, then x would be 0. Because again, there's two parts to that equation line. Remember, there was the line itself, which was b, and then we have a, which is where that line would meet that y-intercept. So this makes sense for this particular study because we're looking at mortality rate of lung cancer to cigarette smoking. So think about that logically. If there were 0 cigarette consumptions, if no one smoked, would there be 0 lung cancer mortality rates? No, because people have, they sadly, unfortunately, get cancer of the lungs, and they might have never have smoked in their life. So this idea gives you that constant for wherever that A is. So that's where this this first part is. The second part, now we're looking at the cigarette consumption per capita, and we're looking at the predicted value, and we have significance where it is 0.01. So this is looking at the slope. It's saying that our slope is statistically significant. Therefore, there is a relationship between cigarette consumption and lung cancer rates. So for every unit of cigarette consumption goes up, the predicted lung cancer rate goes up. So it's basically saying, like, yes, what your correlation, what you found, there is definitely something to this. And that for every time you increase X, our cigarette consumption, then our Y would increase, our mortality rate of lung cancer. And that equation is shown down here. All right, and this is just a brief little example of if we wanted to do it by hand. Here it is, and this would give us the same answers here. And I can show you with this lovely little line. And there it is. Here is our slope, and then this is going to be our A. Yeah, B and A. How BA is that? All right. And moving forward, again, we did, in order to get to that regression stage, we also looked at the Anova which is using a t-test. And we also looked at correlation. So just pointing out that if we were to do this by hand, because we are using our b that we were able to calculate and by our standard error, and then we would get, voila, it is going to be under that, that our t-test. There you go. And then there's our p-value. So again, this, what we're looking at here, I mentioned Anova. I didn't mean to. That was just more of like the assumption to set up everything. We still run a t-test behind the scenes, and we find out that there is significance. And this is how you would write it. Ta-da! All right. Now we go into multiple regression. So whereas we just looked at one thing to predict and to associate with lung cancer mortality rate, now we would look at multiple things. Now, unfortunately, we're not going to use, maybe fortunately, that we're not going to use the same example of smoking and lung cancer. So this is where we now have we have the same continuous or scale variables, quantitative variables, for both our x and y. And again, we're looking at the relationship, but now we're looking at it with multiple x's. So this could be just a laundry list of things that could predict what y is. This is used a lot to find different combinations of variables that might be able to explain our y. So it tells us one, how much of a variance in the dependent variable can be explained by the independent variables. It can also give you an indication of the relative contribution of each independent variable. This is really nice. And it will also determine the statistical significance of the results in terms of both the model itself and the individual independent variables. Okay, so for these conditions, just like last time, it needs to be normal. Everything needs to be independent of each other. One thing that is, now that we're adding multiple independent variables, there is something called multi-collinearity, and this basically occurs when you have two or more independent variables that are highly correlated with one another. So say I was to look at grades associated with reading and writing scores and math scores, and if the reading and writing scores were way too close to each other, if they basically were correlated to 1, which means that all the scores were the exact same across the board, then that's not what we want, because it's basically diluting some of the equations that the software is going to run. All right, once again, here is the equation for the simple regression population. Not really going to mess with that. And here's our equation for the multiple regression population model with all of the lovely lines, so you know what we're looking at. Again, this is the population model, but we're just going to get to the fun stuff. So estimates for the coefficients. Now this is the equation where we're adding in each of the variables that we have, the independent variables. And then in order for us to get the standard error for this, we would want to have the sum of all the residuals that are, and we square that and we divide it by our degrees of freedom. As usual, our 6 hypothesis steps. So we want to look at how well do the two measures of control predict perceived stress. So the two measures of control are mastery and perceived control of internal states, so PCOIs. So we have two scales, and we're using those two scales to help predict this third scale, perceived stress. So these are our X, mastery, and PCOIs, and then our prediction would be the perceived stress. So all scales, all quantitative. Our research question, so say you were to do this for your project or you have an exam coming up, you would put how much variance and perceived stress scores can be explained by scores on the mastery and Pecoy scale. Let's do a quick other example and just change this up a second. So I want to use some like scores elsewhere. So let's try how much variance in grades can be explained by reading and writing scores. Okay, so you're asking how much variance in a certain score, our y, can be explained by our x's. All right, our null hypothesis is mastery and perceived control of internal states, or Pecoys, do not predict perceived stress. Whereas our alternative is that, yes, in fact, the mastery and Pecoys predict perceived stress. So in our example, we will go to, and we have this file that we'll practice. We'll go to Analyze Linear Regression again. And okay, so this is kind of like the funny thing to me, but it makes sense for continuity, is that we have our dependent variable on top and our independent variable on bottom. So like all the other analysis, I just wanted to point this out, that all the other analysis also start off with the dependent variable here on top and then the independent below. However, when we've looked at something like, say, a t-test, you would actually put, or an Anova, we would put multiple groups up at the dependent variable, and there would only be like one down here. So say it would be like a gender down here, and then all of our scores that we would want up here, right? Whereas, remember, we only have one y value that we're looking at, and then we're determining what our independent is. So we go to statistics. We need to make sure that all of these are checked. This time we have the Collinearity Diagnostics. Again, this is going to let us know whether whether these two variables are closely correlated. All right, when we go to plots, we will put in, just like last time, for our y, we would put our z residual, and then for our x, we would put our z predicted. And then for our distance, we would use the Mahalanobis. Let me try it again. Mahalanobis. I always mess it up. Every time I see it, I screw it up, but I'm going to try one more time. Let me try it. Mahalanobis. 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 All right, I always get it. Always get it. Mahalanobis. Sounds like a race car. All right, go to options, and we are going to exclude any cases pairwise. And we start off with our correlation. So we're looking at our correlation between our perceived stress and our total mastery and our total Pecoys. And notice that this is kind of like a reflection. So make sure the pin is on. So you can draw a line actually right here. So notice that this is 1, this is 1, and this is 1. And then this is 0.521, this is 0.521. So they're the same thing. You're actually only looking at 3 numbers here because it's the same thing over here, because we're correlating each of the each of the variables to one another. And so for this, we are going to want our independent variables to be correlated above 0.3, but not above 0.7. So that will let us know whether things are too correlated. And the reason why these are 1 is because it's comparing the total mastery scores to the total mastery scores, which would be 1, highly correlated, right? So you don't want anything too low or too high. We need that Goldilocks. All right. And then we look at our tolerance and variance inflation. So our tolerance, so that's going to be right here. Our tolerance is an indicator of how much the variability of the specified independent variable is not explained by the other variable. So that in other words, we're truly making sure that that these numbers aren't fully, that the independent variables aren't too highly correlated. We're continuing on with that. So again, we're in a range. It should not be it shouldn't be too small. And for our VIF, we don't want anything too big. So we don't want anything above 10. And for our our tolerance, we don't want anything below 0.1. And so looking at this, and so yeah, our answers here, our results, they're good. We're good to go. These are acceptable ranges. All right. So with our p-value or PP plot of regression, we have some pretty strong correlation. It is right down the middle, and even though it sways left or right around the residual line, it looks good. No major deviations. All right, this is our scatter plot. This looks good. Now you might have some like slight outliers right here, but basically what we found, everything looks good. All right, our other assumption is to look for any outliers, which we did look at visually, and this is showing us that this is where we check the Mahalanobis distance, and nothing should be above 13.82. This is slightly above it, but again, based on what we saw here, we're pretty good. Everything's generally scattered. Yeah, you're going to have a few outliers here and there. So again, it should be below 13.82. For this example, it's okay. Our descriptives, when we run our regression, we are again going to get our R value, and so this is going to tell us how much of the variance and in our perceived stress can be explained by the model. And again, our model includes PCOIS and mastery. So our model can change. Say for the other example I had of grades and reading and writing scores, we can change that model by adding in another variable, right? So we're going to get a completely different answer. So for the value of 0.468, which is just R squared, we can say that 46% of perceived stress can be explained from our model, which is, again, PCOIS and mastery. And this adjusted R squared is just a little bit more conservative. And so this is the one that you would probably want to check, but if you put this one, that's fine. So we were at a 0.684, and if we look at this in our fun effect size sheet, it's almost right there, so it's almost much larger than usual. Then we look at our Anova, and we're looking at our F-score, and this is giving us our ratio for testing the null hypothesis. And therefore, because this is significant, we can reject our null hypothesis because we are basically saying that the model that we have of our PCOIS and mastery significantly does predict perceived stress. So, whereas with some of like the Levine's test or the normality test, that was our bouncer. Our Anova is kind of our bouncer in moving forward with our regression. So then we get to our regression, and we find that there is significance among both variables when it comes to our Y value. And so each one gives a different number here, and this is basically your strength. So the higher, I shouldn't say the higher, the further away from zero it is, the stronger it is. So in other words, because this is a negative line, then if it was, it's trying to get to the highest that this could go is negative 0.1. It can also go to 0.1. So this is examining our standardized coefficients. So this is where our beta is. And this means this is the values for each of the independent variables have been converted to the same scale, so that we were able to put whatever scales we had, able to put them kind of in a uniform model in order to compare. And for both mastery and PCOIS, it makes a significant contribution to the prediction of perceived stress. So which one has a more significant contribution? Well, it would be this negative, it would be the mastery scale compared to the Pecoy scale. So in other words, if we were to increase the mastery scores by 1 standard deviation, then the perceived stress scores would likely drop. So in other words, if we were to take that sample of whoever took this survey of Pecoys and mastery, and we were to like take them to all the appropriate organizations to help them out in their life, let's give them a life coach, and their mastery score, if they were given the same question and their mastery score went up by a whole standard deviation, then there's a chance that their perceived stress would drop by 0.442 standard deviation units. And here is the way to explain it. And I just want to go back to make sure I covered everything on this. Yeah, both of them definitely have a significant contribution to the predictive score based on our model, and we're good.